So as a follow-up to my earlier video on adding an automatic drain valve to my air compressor, with a little more time and experience with that, being inside the house in my workshop, I have gotten really tired of it going off every hour. It's just a little too frequently and always startling when it goes off. And not really desirable to have something startle you when you're working with tools that have blades and so on. Just don't need that kind of surprise. I would be satisfied if the thing went off maybe twice a day maximum, which should still, I think, be reasonably adequate for draining the tanks fairly regularly. I've confirmed with Van Air that their EDV 115, which is what I have, does not have another version available with a longer interval. It goes to 60 minutes maximum before the next time the valve opens. But the electronics module can be separated from the rest of the valve and just operate the solenoid from something else. So I thought I'd take a crack at coming up with something simple and inexpensive, and to that end I have purchased a couple of solid-state relays from Amazon, just cheap Chinese ones that have appropriate ratings for the solenoid on the drain valve, and I plan to just drive it off of a simple astable multivibrator using a 555 timer. I figured that'd be the quickest and simplest way of doing it. Somebody younger than me might just immediately throw an Arduino at it or something like that, but I figured, being an old school guy, I'm going to use something that I've used before and see about making that work. So what I want is something with a very extreme duty cycle, where the output's only on, or the valve on the drain valve is only open, or the solenoid energized, it's all the same thing, for about 6 seconds every 12 hours. So a 12-hour interval, and then energize the solenoid and drain the air compressor tank for about 6 seconds. And I probably don't need to make this adjustable, but I'll probably make this one adjustable, just in case I decide I want it to, drain for 10 seconds or something. That should be pretty easy to do, but I don't need great precision on this. It's just I don't want it going off every hour, and this will be, even if I get it in the ballpark of 12 hours, it should be fine. It doesn't need to be synchronized with the clock or anything. Here is the classic 555 timer astable multivibrator circuit. The chip needs V+, and I'm going to design this to run off of 5 volts just for the convenience. I don't have to build a power supply for it. I can just grab any of the ubiquitous USB chargers that are a few dollars a piece, and I probably have a bunch in a box anyway. Cut the connector off the end and just use it to power this little circuit. That just makes it convenient. So, but the 555 doesn't really care what its voltage is as long as it's not really high. So we have, say, 5 volts connected to pin 8. Ground is on pin 1. There's a reset function which can force the output to be low, as I recall. And if you don't want that to happen, you have to pull the reset up to the same voltage that the V+ is, in other words 5 volts in this instance. There's an internal voltage divider from pin 8 to pin 1, dividing the power supply voltage into 3 equal parts. And traditionally they are 5K resistors, so 3 5K resistors which is purportedly the reason why the chip is called the 555, from those 3 5K resistors that are instrumental to the way this thing works. Anyway, one of the junctions in that voltage divider is brought out to pin 5, and you can hang a capacitor there optionally to stabilize it for more stable operation, especially if the power supply voltage moves around a lot. Most times you don't really need it, but it doesn't hurt to hang a cap off there anyway. So the way this usually works is you've got a flip-flop inside of there, and it's controlled by the voltage on a threshold input. So you basically have 2 resistors in series, we'll call them RA and RB, and those are going to a capacitor which is connected to ground. And when the 555 starts out, let's say it's trying to charge, it's in the position or internal flip-flop position where its output is turned on. And when that happens, this transistor here, which is connected to the discharge pin, pin 7, that's open, so it's like nothing's connected here, and you're basically charging capacitor C through the series pair of RA and RB. And it's a very simple calculation to figure out how long it's going to take for this capacitor to charge up to the threshold voltage. And when it does, then the internal flip-flop flips to the other state, the output goes low, and this discharge transistor turns on, essentially tying this point to ground. So it's like this resistor isn't doing anything, and now this the charge on this capacitor discharges to ground through this resistor only, and then back to ground through this transistor. So, and then once the voltage on the capacitor goes below a threshold, then the flip-flop flips back to the other way around. This transistor turns off, so it becomes an open circuit. The output turns on again, and you start charging again. So it's repeating. And you can easily calculate, as I said before, the charging time is dependent upon a RA and RB charging capacitor C, and the discharge time when the output is low depends only on RB and C. Now, because in a normal configuration like this you can't get away from the fact that the charge time is going to be longer than the discharge time, so it can't even get to a 50% duty cycle without pulling some sort of tricks. And I actually want the on time to be shorter than the off time, and shorter by a lot. 6 seconds on versus 43,200 seconds, which is 12 hours, off. So I actually want the duty cycle to be upside down from the way the 555 would normally have it. So to reiterate, on this waveform I showed, the time when the capacitor C is charging determines the length of the pulse when it's high, and the time when C is discharging determines the length of time between pulses when the output signal is low. Now, to get more flexibility in this, to be able to dial in the charging time and the discharging time in isolation from each other, so you don't have to, for example, consider both RA and RB for charging and only RB for discharging, you can modify this circuit a little bit. Okay, this is the way we do that. Pretty much the same circuit, but we've added 2 diodes to it. That's the only change, really. So, whoops, I forgot to draw on the capacitor. Let's get that guy in here. There we go. So, with these diodes on here, When we're in the charge cycle, or the charge part of the cycle, the output is turned on, the discharge transistor is turned off, so this point is open, and we have this diode pointing in this direction and essentially shorting out resistor B and diode 2. So when we're charging this capacitor, it comes down through RA, it bypasses this stuff by going through diode D1 and then charges the capacitor. So the charging time is dependent only on resistor A and the value of the capacitor. These parts don't have anything to do with it. So it's real easy to do the calculation for the charging time. Then, during the time when the flip-flop is flipped and the output is low, and this transistor is turned on, making this point essentially ground, as before, this resistor now is basically between V plus and ground. It basically does nothing. This diode is reverse biased because now there's a charge on this capacitor. It's a higher voltage than the voltage at ground, which is 0 volts. So this diode does nothing. And now you discharge this capacitor through this resistor RB to ground, and because this diode is forward biased, it allows that to happen. So essentially RA and C are what dictate the charging time, or the time when the output is on, and RB and C determine how long the output is off, or the capacitor discharging time. So it's very simple. Just take the normal circuit, add a couple of diodes in these positions, and that should work. Now, at this point, there's no reason why RA and RB, their values could be flipped. You could have it so the output is short, and the it's short when it's high and it's long when it's low. Or you could flip it around the other way and have it be high most of the time and low just a little bit. So it all depends on how I connect it to the optocoupler. But again, all I need to do is swap those two resistor values, and I can make it behave the opposite way around. So there's a couple ways I can do this. The opto isolator, or the solid state relay, is basically, from our perspective, it's just an LED and a resistor. So I could connect it with that internal LED and the solid state relay's internal current limiting resistor for the LED. So whenever the output is low, it's pulling current through the LED and turning it on, thereby turning the output of the solid state relay on and ultimately energizing the coil of the drain valve. Or I could have it source the current, so instead of this, pretend like this isn't here, I could I'll put a dash box around this. So this is the same circuit. This is what's on the input of the solid state relay. Here's the same thing drawn again. The difference is that the and this is probably called the plus side. This is probably called the minus side. Same thing, plus and minus. So it just depends whether you wire the plus input of the solid state relay to the plus 5 volt signal and the minus of the solid state relay to the 555, or if you connect the plus of the solid state relay to the 555 output and the minus of the solid state relay to circuit ground, then it'll work just opposite. So you can wire the solid state relay either way to get the desired duty cycle, or you can flip these two resistors to get the desired duty cycle. Works either way. Normally I like to have things like this have their current sunk by the by the output, but the 555 can work either way, and it's good for up to 200 milliamps, which is way more than these are going to use. These are probably more like 10 milliamps or something, so we're not stressing the output at all. I haven't yet decided which way I'm going to do this, but it doesn't change the calculations or the circuit design. For the next part of my description here, I'm calling this part of the output T1, time period 1, and this part I'm going to call it T2 or time period 2. And again, we're talking about 6 seconds for T1 and 43,200 seconds for T2. Here's the normal formula for calculating T, where T, not T1 or T2, but T meaning the period of the entire cycle, so from like the beginning of this all the way to the beginning of the next one. That would be T. So I guess I should probably like that. So T would be a constant of 0.8 times the sum of resistor A and resistor B times the value of the capacitor C. Now if we just want to figure out in this circuit just the T1 or the T2 part, we can say that T1 equals 0.8 times what I say, that was during the charging time, so that would be RA times C. And T2 equals 0.8 times RB times C. There's my air compressor going off downstairs. I'm right upstairs from where it is you can really hear it. Luckily the rest of the house isn't that way. You can barely hear it there. It doesn't wake me up when I'm sleeping. Alright, so I've got my little formulas here. Well, what I'm trying to do is figure out what the values for RA and RB are, given these times that I've determined. And so we can use simple algebra to flip these formulas around. So RA equals T1 over 0.8 times C, and RB equals T2 over 0.8 times C. So that's how we rearrange the formula to solve for the resistors. That means we have to know what C is ahead of the time, and I've already established I'm going to use a 1000 microfarad capacitor for this circuit. So fill these guys out, and you end up with 6 seconds over 0.8 times 1000 microfarads, and 43,200 seconds over the same thing, 0.8 times 1000 microfarads. And that ends up being RA equals 6.8 K, that's kilo ohms, and 49 mega ohms, which is a lot, but it's not astronomical. Now, it's not usually advised to run 555 timers with really high resistance values, so I'm going to have to prove this out empirically to make sure there's no issues with leakage or something stupid that's going to really mess up the way this operates. If it does, then because I've got such a long time delay, if I want to make this, for example, 5 mega ohms, drop it by about an order of magnitude, then I'm going to have to jump up to 10,000 microfarads, which is a lot. So I'm inclined to try to make it work with the larger resistance value. 6.8 is no problem at all. And basically just try it out. I haven't established yet how I'm going to check it, since it could be off quite a bit due to component tolerances and things. I don't really want to sit there and watch the darn thing for 12 hours to see if it cycles, but I'll figure something out. Well, this sounded good until I thought about it a little bit more. This would work great with the 555 in this circuit, coupled with a solid-state relay to control the solenoid, but not over the time period that I'm dealing with here. 12 hours is way too long. Reading the data sheets on the 555, the such large values as 10,000 microfarads, for example, that I was thinking about, or even 1,000, might be a little big. That forces you usually into electrolytic capacitors, which usually have too much leakage if you're charging them very slowly, which we would be, or discharging them very slowly. And the maximum recommended resistance with RA and RB, or in my case either one because of the way I'm using it, is really only maybe 5 megs or something, with a 5-volt power supply. So this is way too big of a value, and even if I dropped it by an order of magnitude, I'd still be a little bit over on the resistance, and that would force me into like a 10,000 microfarad cap, which probably the leakage would be so high that it wouldn't operate reliably. So while this is a good idea and the circuit is basically sound, it's not going to work in this application. The time delay is just too long. Now I could gussy it up by doing a different circuit, maybe something to handle the longer part of the time with some digital circuit, but then that gets complicated, and I'm thinking of a different solution. So I'm thinking of a small smart relay, or Micro-PLC, or Pico-PLC. Would be a bit of an overkill for this, but it would work, I think. My favorite brand when it comes to those things in terms of affordability and ease of use is the Tico brand out of Japan. And in the US anyway, the place to buy those is FactoryMation, which is factorymation.com. And they're fairly inexpensive. The SG2 series is what we're talking about here. They call it the PLR, Programmable Logic Relay, or Smart Relay. You can buy these in several flavors. You can buy the full-featured one with an LCD display and a little keypad. You can program it using this and you don't need anything else. Or you can get the OEM blind one, which is the same deal but without the screen and the buttons. This is if you're maybe producing a product that uses a lot of these. You want to economize a little bit. You might go from, say, 90 bucks for the full-featured one to maybe 75 bucks for the one without the keypad and LCD. The rest of it's the same. Or you can go with the OEM bareboard one that doesn't even have the case. It just has the bottom of the case, doesn't even have the top. It's just the circuit board, really. So these things are just a little microcontroller They've got some optically isolated digital inputs. Some models have analog inputs. There's relay outputs on them. I think they all have relay outputs. You can get ones with 4 outputs. You can get ones with 8 outputs. You can even get little HMI human-machine interface products and expansion modules and things, but it's pretty basic stuff. I happen to have a number of these that I bought years ago just to do random projects with, and I've used a few of them over the years. This is the model SG220CRA. This is a 12 digital input unit that would be on this top terminal block, the green one, and they're also and all 12 of those are for AC inputs, 120 volt AC, for example. And then it has 8 relay outputs. I only need 1 if I'm going to be running this solenoid on the drain valve, and they're all relay type. So 12 AC digital inputs and 8 relay outputs, no analog, and the unit runs off of 120 volt AC. Actually, I think it's in the range of 85 volts to 265 volt AC power. So quite a wide range. This is one I had set up to use for something else. It was just going to be a light flasher for something, I don't even remember what. And I pulled it out of the box and turned it on, and it starts clicking every couple of seconds. It was doing something like that. I believe I was actually just using this as a demonstrator. I was going to install this in a building that I was doing some volunteer work at, and then we changed our plans. So it's still programmed to be doing that on and off thing. And the nice thing about this Pico stuff is that the programming software is free. The SG2 programming software, you can get it for free, or if you want to get it on a CD-ROM or something, you can pay $8 for the disc, but you can just download it from the Factory Mation website. And so I also bought the, I think it's $8 cable, which plugs into the circuit board, and then it goes to a USB connector on the same computer the software is running on. And I just told it to go online and told it to use the COM3 port. And you can see the program here in ladder logic. And the magenta tells you what's turned on logically. So right now it just has 2 timers, one for the on delay and one for the off delay. And then the output of the first timer controls the output relay, which is called Q01 here. So I can hover the mouse over T1 . It looks like it's set up as a 2-second timer. I can hover the mouse over T2. It looks like it's also set up to be a 2-second timer. So it's doing a 1, 1000, 2, 1000, 1, 1000, 2, 1000. Yeah, so a 4-second cycle, 2 seconds on, 2 seconds off. Very simple piece of logic. It's basically what I need to do for this drain valve solenoid. I just need to change the values. But I'm pretty sure that I won't be able to do it this way because I think the maximum time on here is, with 4 digits in seconds, I can't get nearly enough seconds. So I would have to do something cute with a counter, and I don't remember if this little PLC even has a counter, so I need to investigate that. Well, it looks like I can do it, and there are counters, but I shouldn't need to. And then we go to timer 1, which is set up as a type 1 timer. That's up here. Type 1 means it's a time delay on. So when I energize the input, it starts timing, and when the accumulator, that's the value in magenta, reaches the preset, that's the value in black, then the timer is complete and its output turns on. The 4 here refers to the time base. It's the 4th time base. You can have very short time bases, like 0.01 seconds. I think that's type 1. Type 2 is 0.1 seconds. Type 3 is 1 second. Type 4 is 1 minute, if I remember correctly. Certainly type 4 is 1 minute. So this is 720 minutes, which is 12 hours. And then when that's done, it's going to energize or close this contact, which will energize timer 2 and start it counting. It has a type 3 time base, which is seconds, and a preset of 6, so 6 seconds. And then that's going to go, and when it times out 6 seconds, the T2 contact up here, which is normally closed, will open, and that resets timer 1, which de-energizes timer 2, which resets it, and the whole thing starts all over again. In addition, the timer 1, which closes after the 720 minute time delay, will also energize Q1, which is the first of the digital outputs, or the first relay output. So that will be energized for the 6 seconds that timer 2 is operating. I don't know if it's strictly necessary, but I'm going to try to fill in the empty gaps here, see if it'll let me do it. Yeah. Okay. So I've got my program there. I've got only a 1 minute in there just for testing. This product is offered in several flavors. One is the same thing you've got here, but with a complete case around it, and then it has a small LCD display and a small keypad for entering and modifying programs. And then there's the OEM version, which still has the case but doesn't have the display and the keypad. You have to program it using an external computer. And then there's the OEM bare board version, which is what I have here. It dispenses with the top case but is otherwise the same. These all just reduce the cost. This particular model, and there are quite a few variations, there are ones with more or less input circuits, discrete and analog. There are versions with between 4 and 8 relay outputs. That's the only kind of outputs they have, I believe. There might be a transistor output version, but mostly they're relay output versions. I don't think there are any with thyristors. If you're going to run AC circuits like 120 volts or 240 volts, I think you pretty much have to use the relays. And then there are versions that are powered off of 24 volts DC or universal inputs like 85 to 260 volts or something like that. This is the AC model, and it's the version with a dozen digital inputs that can be anywhere in the range of the power supply. So in this case, the high 80s up into the mid 200 volt AC range. They're all referenced to the AC common, so there's no common on here. It's just the 12 input points where these screws are. And then the outputs, they're just isolated, so every 2 screws is on a different relay circuit. I have it plugged in with the proprietary cable into a USB port on my computer. AC power is hooked up, and going back into the programming software, let's go online here with the PLC. This is all just being viewed offline. This is the program I've saved on my computer. If I go up here to operation, I can go down to link COM port. I know that my USB from the device manager in Windows, that the USB cable I'm using is considered to be COM3 at this time, so I've already got that selected, and I just say link. It confirms that it's successfully linked between the desktop computer and the PLC here. Do you want to read program data from the module? That's only necessary if you don't currently have a program loaded in from the computer and you need to load it in from the module or the PLC. The software refers to it as the module. Or if you've made some changes and you're not sure the two match up, they need to match up. In other words, the two versions, the one on the computer and the one on the PLC, need to match up in order for it to properly show you the status up here. So I know that they're the same, so I'm just going to say no. And now the magenta shows what is logically true at a given moment. So T02 being closed normally is at a logic 1 state. It goes all the way up to here, and when I ran this a little earlier, I was up to the 25-minute mark, and it remembered that. So if I sit here and wait long enough, I should see it kick over to 26 minutes from status. Oh, okay, it just changed over to 26. So we know that timer's working. But it's going to take a long time before it gets to 720, right? Anyway, I won't be able to show it operating the rest of the logic here because it's going to take too long. I'm going to wait again for it to go up to 27 minutes just for further evidence that it's working. There we go. So we know that's working, and according to the manual and TECO tech support, it can go up to 9,999 minutes. There's no restriction on it being a lower number. It can go up to the full number you can represent in 4 digits of decimal. So I'm going to stop this, and I'm still online, but I'm going to do my edits offline. The first thing I want to do is I want to change timer 2 here. I double click on it and opens up my edit dialog box. It confirms that I've got timer 2, that it's a mode 1 or a type 1 timer, which means on delay timer. It shows the waveform for the timer. When it's enabled or energized, then you have to wait the time delay value before the output turns on, and then the output stays on as long as the timer is enabled. Whenever the timer is disabled or no longer enabled, then the output also becomes disabled or off. You can hear my compressor down in the basement just kicked on. I'm sure that I have it set to only about 3 seconds or so currently, but since it's going to be activating for only every 12 hours, I want it to be on for a bit longer. So right now I'm planning on having it be the 6 seconds. So now here I'm confirming that I have a 1 second time base selected. That's time mode or time base mode 3, even though it doesn't show it here as such. The preset value is currently 2. I'm going to edit that and make it 6. Preset type is N, just means it's a non-variable. It's a fixed value that can only be changed the way I'm doing it here. It can't be changed from within the program. So I say OK, and the new time base is reflected up here. Meanwhile, this guy is down to 0 because it's not currently running. If I were to, well, I'll show what happens when I go back into it. But I'm going to be driving the solenoids directly off of these relays, only one relay at a time. Their rating is more than adequate for the solenoid on the compressor drain valve. Here's the typical relay. On the side of it, it's only giving contact ratings assuming 240 volts AC, and it's 8 amps. That's probably a resistive rating, so we might want to derate that to about a third. Let's just say a quarter to keep things simple, so 2 amps inductive loading. And then the actual solenoid only takes about 0.3 amps. So this relay should be more than adequate, or any of these relays should be more than adequate for the load of the solenoid on the drain valve. But just in case one of these should ever burn out or wear out its contacts, without having to reprogram this, I'm planning on programming it to operate all of the lowest four relays in parallel, so that if I need to, I can just move the wires over to another relay should it stop working reliably. I can confirm by just looking at this little mini manual that comes in the box that there is a transistor output version of this. Otherwise it's relay outputs. And confirming that it's numbered left to right on the 4 relay models. So relay 1 on the left, 2, 3, 4, 5, 6, 7, 8. So I'm going to be doing these left 4 relays all in parallel. With this software, it's fairly easy to do. I'm just going to go down to my timers here and click that. So now wherever I move the cursor, we'll do something relating to a timer. I've already got output Q1 in there. I'm just going to make 3 more rungs just like it. So I placed it. This time it's still going to be timer 1. It's going to be a normally open contact. So I've got one there. I'm going to put another one down here. It's timer 1, it's normally open. And one more. Timer 1, normally open. Now I'm going to put an output. So I select the Q outputs down here. And this is good for placing either contacts or coils of outputs. And you can have contacts off of outputs if you need to use them in the circuit or in the logic. So I'm going to go up here and place one, and it wants to know which Q. This is going to be Q2. So there's Q2. Q3. Q4. Okay, I've got all those in there. Now I have to go down here and click on the thing that makes the rung links. And there we go. I still have my timer logic. I'm verifying that I have a mode 4 timer at 720 minutes and a mode 3 timer at 6 seconds, and that whenever timer 1 has elapsed for the 6 seconds that timer 2 is running, any contact labeled T01, that's these 4, is going to be on, and it'll energize Q1, Q2, Q3, and Q4. So I'm going to go up here and save my work. And I'm still online. So I'm going to go back to, I have to save this program to the PLC, so I click on write. The old data in the module will be lost. In other words, I'm overwriting it. Successful. And now I can put the unit in run. Do you want to read from the module? No, I don't need to because I just wrote to it. Okay, so my top rung is true automatically because of the normally closed contact. And up here it shows that my first timer has reset. It always goes back to 0 whenever you take the processor out of run. So now it's in run mode. I'm going to wait to make sure it goes up to a couple of minutes. So I'll sit here and chat and do an edit or two. And it's about 8 o'clock, so I have to set my alarm for tomorrow morning, maybe around 7:30 or so, so that I can get up in enough time to make sure that I can actually see the relay outputs turning on at the requisite time. I want to make sure I can see one cycle, and then I'll feel good about putting this there. I just kicked off 1 minute. But I don't want to get up at 8 o'clock in the morning. I plan to sleep in the morning, so I'm going to take this back out of run. I just stopped its execution again. Just for good measure, I'm going to do a save. So my program is now the way I want it, and probably around 9 o'clock, it's still 8 o'clock, in about an hour I'm going to put it back into run, and then just leave it run overnight, set my alarm, and get up in time to watch it cycle once. Okay, it's about 9 o'clock at night, so I have a good idea when this guy's gonna time out. I'm still online, and I'm gonna put this guy into run. Did it go into run? Oh, maybe it timed out. Oh no. Yeah, there we go. So now it's running right at 9 o'clock. I'm going to wait to make sure it times out to 1 minute so I know it's running for sure. There we go. So I'll just revisit this in 12 hours time. So here's the timer and the valve as shown in my other video. Let's see if I can get it off here. Yeah. So that's just the incoming power cord here, and then the socket here that goes into the actual solenoid. I'm pretty sure this middle one's the ground. Yep, that middle one's the ground. So ideally I should carry that through in my wiring. I want to connect that up to ground. And then these outer two ones are obviously the coil. About 110 ohms thereabouts. And those do appear to be just regular push-on connectors, so that should do the trick. That's just to confirm the wiring on this. So this is the incoming power cord on here. There's a gasket and then there's a plug, and it has the same two AC plugs and the ground on either end, so you can plug it in either way around. Now if I just stick it down here right on the solenoid, proof of the pudding. Okay, it's 8:58 in the morning, and I come over and check the logic execution, and the accumulator on T1 is up to 718. Okay, just switched to 719 at 22 seconds on my watch. And although I'll only have 6 seconds to watch it, I'm going to try watching this because there's not really anything to see down here. It'll just make a clicking sound. So we'll get more satisfaction, I think, by watching this. See if I can get my timer status back. Any second now. Heard the relays click. You can see all these rungs turned on now. They're energizing all 4, and the timer just timed out and reset. Everything's back to normal, and it's starting another cycle of 12 hours. Notice how the accumulator up here reset to 0. I'm going to watch it tick over to 1 second. There we go. So the logic is working fine as expected. I definitely heard the relays click here, so that's all good. Now it's time to wire this guy up. Alright, there's a few things I picked up at the hardware store to facilitate this modification. I have some push-on connectors. I got a 6-position terminal block. I couldn't remember if I had any in my parts bin, so I bought one just in case. This is kind of a beefy sucker, but I figured I would need a power distribution block to make this work. And I have a 6-foot general purpose power cord with nothing on the other end, just the bare leads, and a grounded plug there, so that should be adequate. And then some of these Rubbermaid take-along plastic bins just to put the electronics into in order to keep the dust and spiders off of them. Well, this is alarming. Once I get these Rubbermaid things out of the packaging, which completely surrounds the part of interest, I didn't realize these things had a barrier in them. I thought they were just a dish that would you know, have this whole area open. Well, these things ended up being a total disappointment in regards to this project. I'm sure they're fine for food. The plastic is much too brittle. I couldn't even carve those out. I thought I might carve out the partition and glue something over that joint, but that would have been kind of an abortion, and I think I can do better. But in the meantime, I'm going to figure out exactly what I need. So I've made up a wiring diagram here. I am going to use this 6-position terminal block. I did not have anything satisfactory in my junk box. So I'll have an incoming AC power cord here, just from my pile of scrap cords. I've cut off the ground on this one, but I'll cut that back a little bit. That'll be the incoming power. That'll be this cord here. I'll put the hot on the first terminal, neutral on the second one, ground on the third. I'll have this fuse holder with a, I forget what this is. It's a little bit oversized. I think it's an 1.5 amp slow blow fuse. So bigger than it needs to be, but still it'll blow if there's a short or something. So I'll have that in there. This will be the fuse holder. I'll tap off the hot, go through the fuse, and come back to the 4th position on the terminal block. Then I'll have this little red neon bulb from my junk box. This is set up with a resistor in it, so it's all ready to go for 120 volts. And that'll be tapped off of the downstream side of the fuse, and the other lead will go back to the neutral terminal. Then on this side of the terminal, I'll take off the fused hot here and go to one of the AC terminals here, and the neutral going to the other terminal on the SG2. Then I'll take another wire off of the fused hot and come around here and go to the first relay contact, come out of that, go back to the 5th position on the terminal block, and then I'll have a cord that actually, this is the cord that I bought at the hardware store. This is the one I'm going to use for the incoming power. It's this other one here, the black one, that I was going to use. I'm just going to cut off the plug here. I'm going to use that as the just for the cord, and that'll be the one that goes out to the solenoid. So its hot leg will go to here. That's the output from the relay. The neutral will go back to the neutral terminal here, and the ground will go to the ground terminal. So the ground just passes through. So that's all the wiring that's going to be in the box. I briefly thought about adding another neon bulb to this, sort of as a sign of life detector. Since the time delay is so long, I thought about going back and programming this so that another relay would click on and off and energize another neon bulb, perhaps on a 1-minute basis or something, so that I could, more readily see that this thing is alive. And I kind of kicked it around and thought, I don't know. I don't think I really need it. And if I do change my mind and decide I just don't know if this thing is alive or not, I can always go back and change the programming and add a little bit more wiring. So it's not like it's a final decision, but for the moment I think I'll just trust that it's going to work. There's no reason to believe it won't. So I have to go on a spelunking trip, I think. Go up and brave the near zero temperatures outside, and I don't even know where I'm going to go. Try to find some sort of a, ideally it'd be a small metal box, but I can't think of any stores in the area that would carry that. And I don't have any project boxes that are big enough. I don't really feel like making something out of wood. And actually, this is going to be sitting on the floor, and no, I'll make it out of wood if that's the last resort. But I'd like to buy something off the shelf for this. Something not made of wood, ideally. I know that the Ace Hardware doesn't have any boxes because the closest thing they had were these things. Possibly the Home Depot, or maybe even a craft shop might have something. So, got to go and do a little bit of a drive, I think. Well, this is what I ended up getting at the Home Depot. They were practically out of stock on all the stuff I really wanted, but I think this will work. It's unnecessarily deep and a little bigger X and Y than I'd really like, but it'll fit and I think it will do the job. So the first thing I want to do is reinforce the plastic here in a couple of places so that I can better mount the cable feed-throughs. So I'm going to make a 1/4-inch plywood piece that'll go up against this area and have an extension up in this area, and the terminal block will mount here. The 2 power cords will come through, so this will help with the strain relief. The fuse block will go up on the extension, give it plenty of space from the terminal block, and keep it accessible near the top of this thing. So I'll just cut that out now and drill the holes. Alright, I've got holes drilled in the plastic. The piece of wood is cut out, holes drilled in it, both pilot holes for the sheet metal screws and clearance holes for the pass-through bolts. Okay, terminal block and fuse holder mounted on the wood. And there is that assembly mounted with 4 632 bolts and nuts. And I've mounted my red neon lamp on the other side of the box, which will be the front. I've marked out a couple of brackets to glue to the bottom of the box and help hold the module centered. Well, I tack these 2 wooden brackets to the bottom using hot melt glue because the bottom kind of sags and it would be very hard to get any other kind of glue that really fill the gap and so on. And then I just squirted a bead of hot melt glue along the outside edge as well, and I think that'll work to hold it in position. It just sort of sets down in there. Not going to slide around, but it can be easily lifted out. So now to wire this up. Okay, I've put on my wire zip tie strain reliefs on the incoming and outgoing power cables. Alright, I think assembly is complete on this. I've got my terminal block wired down there, fuse holder, incoming and outgoing cables, a couple of twisted wires going over to the neon lamp, a red and a black wire coming from the relay contact and going to the terminal block. And then at the far end of the black cable I have my 3 push-on connectors to go to the solenoid. I've used the programming software to print out a ladder diagram printout. I didn't put in any of the comments, so I just wrote them in by hand to remind myself how it works, what it's supposed to do. Have to remember to put the fuse in or it won't work. Come on. Hard to do this left-handed. There we go. And I've got my wiring sketch and ladder diagram printout. Have that folded and tucked inside. And I'm going to take the original timer and just lay it down inside of here in case I want to go back to using it again. And I've also tucked the original power cord into here. Won't do any harm, and again it keeps it around in case I want to revert to the original timer. Okay, there's the final product. Whoops. Shouldn't have tipped it over that far. Okay. Cover snaps on. I'll move it into position now. And the push-on connectors are on the solenoid. So for testing purposes, I'm just going to leave this out here on the floor. And I'm going to put this cardboard box in the way of it. So I can come down in about 12 hours. Well, 12 hours from now it's about 2:15 in the afternoon, so that'd be when I'm sleeping, but I can come down tomorrow morning, and if the box is blown halfway across the room, I'll know it worked. Okay, I'm going to plug in the power cord. And I got the light, so I know all is well and the fuse is not blown. That's really what the light is for. And then we'll see what we see tomorrow morning. Alright, I come down in the morning, and the telltale box is way over here. This guy worked. Freezing rain overnight.